Double the input to a resistor, and the output doubles too. But do the same thing to a diode or transistor, and the response may change completely. So why do some circuits behave predictably, while others create entirely new effects? A linear circuit is a circuit whose output changes proportionally with its input. If the input voltage is doubled, the resulting current or output voltage also doubles. This predictable relationship makes linear circuits much easier to analyze because their behavior follows simple mathematical rules and remains consistent across different operating conditions. One important property of linear circuits is the principle of superposition. This means that if multiple independent sources are present, the total response can be found by adding the individual responses caused by each source separately. Engineers rely heavily on this property because it greatly simplifies circuit analysis and design. Ideal resistors, capacitors, inductors, and many small signal circuit models are treated as linear elements. These components form the foundation of classical circuit theory and allow engineers to develop powerful analytical techniques that remain useful throughout electrical engineering. A nonlinear circuit does not respond proportionally to its input. Doubling the input does not necessarily double the output. Instead, the relationship between voltage and current may change depending on operating conditions, making the behavior more complex than that of linear systems. Many practical electronic devices are inherently nonlinear. Diodes, transistors, LEDs, and semiconductor devices all exhibit nonlinear voltage-current relationships. For example, a small increase in voltage across a diode can produce a very large increase in current, especially after the device reaches its conduction region. Because of this behavior, nonlinear circuits cannot generally use superposition or many standard linear analysis techniques. Engineers often rely on approximations, numerical simulations, or operating point analysis to predict how these circuits will behave under different conditions. The distinction between linear and nonlinear behavior affects how engineers analyze and design systems. Linear circuits are predictable and mathematically convenient, making them ideal for understanding fundamental concepts and building analytical models of complex systems. Nonlinear circuits, however, are responsible for many of the most useful functions in electronics. Amplification, switching, signal detection, rectification, oscillation, and digital logic all depend on nonlinear behavior. Without nonlinear devices, modern computers, communication systems, and consumer electronics would not exist. As a result, engineers must understand both worlds. Linear models provide simplicity and insight, while nonlinear models explain how real devices achieve practical functions that cannot be produced using purely linear components. In practical engineering, many systems contain both linear and nonlinear sections. A communication receiver, for example, may include linear filters and amplifiers alongside nonlinear mixers and detectors. Each section is analyzed using techniques appropriate for its behavior. Engineers often use linear approximations, even for nonlinear devices. Around a specific operating point, a nonlinear component can sometimes be treated as approximately linear for small signal variations. This approach, known as small signal analysis, is widely used in analog and RF engineering. Understanding when linear assumptions remain valid is a critical engineering skill. Incorrectly applying linear analysis to strongly nonlinear behavior can lead to inaccurate predictions and poor system performance. Linearity is especially important in RF systems because communication signals often contain valuable information that must be preserved. A highly linear amplifier can increase signal strength without significantly distorting the transmitted information. At the same time, many RF functions depend intentionally on nonlinear behavior. Frequency mixers, modulators, demodulators, and signal detectors all rely on nonlinear devices to create new frequencies or extract information from incoming signals. These operations would not be possible in a purely linear system. This balance between linearity and nonlinearity lies at the heart of RF engineering. Successful designers must know when to preserve signal integrity through linear operation and when to exploit nonlinear effects to perform useful signal processing functions. So today, we learned that linear circuits produce outputs proportional to their inputs, while nonlinear circuits can create much more complex behavior that depends on operating conditions. Both types of circuits are essential in modern electronics, and understanding their differences is a fundamental step toward advanced analog and RF design. In the next lesson, we'll explore Thevenin theorem and learn how complex circuits can often be simplified into surprisingly simple equivalent models. If you found this useful, like the video, subscribe, and follow for the next lesson.